Let's continue our quest to solve the 1D Helmholtz equation with finite elements, and we're on to step 2, which is trying to approximate the unknown function. So we're doing that element by element. So let's say you have an element with a certain beginning and a certain end. So let's call the beginning x1 and the end x2. Strictly speaking, if we're working in elements L, we should call this x1L and x2L, but in order not to make the notation too heavy, I'm not going to write these indices here. Okay. So we have an element with a beginning point and an end point. By the way, these points, they're typically called the nodes of the mesh. That's just some extra piece of terminology. And let's now try and figure out how we're going to write the unknown fields as a certain sum of basis functions in this element. But before we're talking about basis functions, let's perhaps take one step back and think about what we would like to have. Let's say that we're going to try and approximate the field such that it varies linearly between the endpoints here. So let's say that we start from a certain value over here and we go to a value over there, and we would like the field to vary linearly between these two values, which we will call psi1, L, we're not going to write the L, and psi2. So this is what we would like to have, this linear interpolation between the values at the endpoints. Now we can write down what that means. So the field in our element L, if we have the linear interpolation, then we can write that as x2 minus x divided by x2 minus x1 psi1 plus x minus x1 x2 minus x1 psi2. So this is obviously a linear function. The question is, does it vary linearly between these two endpoints here? Well, to verify that, just simply plug in, for example, x equal to x1. So if x is equal to x1, then this second term vanishes. This guy over here, this prefactor, becomes 1, and we do indeed end up with psi1. And likewise, if we substitute x equal to x2, then this first term vanishes and this second prefactor becomes 1, so that indeed we end up with psi2. So this is indeed a linear interpolation between these two end values. The question is, how do we then frame this in the language of basis functions? Well, simple question. Pause the video and think about what the basis functions would be in this particular case of linear interpolation. It's pretty straightforward in this case. So here we have, for example, our first basis function b1 of x, and then psi1 is our first unknown, and then the second basis function is this thing over there, and the unknown here is u2. So this is just rephrasing this in the language of the general recipe that we had earlier. In this particular case, there's also a very clear physical interpretation behind these unknown expansion coefficients. Namely, they are the values of the field at the nodes of our elements. Just for fun, we can sketch these basis functions. So if we have x1 over here and x2 over there, and this is 0 and this is 1, well then basically these basis functions, they vary linearly between 0 and 1 at these endpoints here. So b1 has a minus x over there, so that's the one that decreases, and b2 is the other one. So these are the shape functions, the interpolation functions, or the basis functions, if we're working with linear interpolation between the values at the edges of the element. Final tidbit here, remember these elements can have different sizes. So in order to make the formulas a little bit more homogeneous, people typically like to work with reduced or local coordinates. If you have a coordinate transformation, let's say psi is equal to x minus x1 divided by x2 minus x1, then this transform coordinate will run from 0 at x1 to 1 at x2. And in this way, you can sort of like generalize the formulas a little bit and shield them from the fact that the dimensions of the different elements could actually be different. But that's a small implementation detail.